Welcome back to NE 630 reactor theory. Before continuing on the business that we used to do last lecture, a couple of students asking me about the homework problem, and I think more specifically about the problem number 1, I think, or number 2. So if you have a spherical shell like this, and this is the origin here at 0, and the spherical shell with radius r, and of course r can go to infinity. So you will solve Laplace square phi minus 1 over L square phi equal to 0. Then your solution 5r will be some c1 e to the power of r over L divided by r plus some c2 e to the power of minus r over L divided by r. So this is a general solution whether you will solve it inside or outside. So we have two regions, region 1 and region 2. So region 1, region R1 is just defined as r small is less than r capital, which is the radius of the circle, and greater than 0. So in this region here, you have to have finite flux. What do we mean by finite flux? Flux does not go to infinity at r equal to 0. So phi finite, I will pick it up as phi at r equal to 0 is equal to 0. If you try to substitute here 0, and then e to the power of 0 is 1, e to the power of 0 is 1, r will cancel with r, and you will have c1 equal to negative c2. You have to transform the equation to sinh and cosh, so it will be most probably sinh. So the flux will be something like c multiplied by sinh function divided by r. So let's say this is the first constant. Then when you will solve the equation in region number 2, which is r is greater than capital R, you will have your flux goes to 0 when r goes to infinity, and this will eliminate which one? C1 will go to 0. Then you will have another phi of r will be equal to C2 e to the power of minus r over L divided by r. So you have two unknowns here that you want to calculate. Then you will have the interface condition. And what's the interface condition? Interface condition tells me that the flux here at the interface between the two surfaces, of course this is a very thin shell. Otherwise you have to define what's the distance here, d. So we will consider it like a very thin shell, so you do not have this double layer. Because we do not know what's the... So you have to know that at this interface, your flux at r equal to r minus. R minus means that you are here in this region should be equal to the flux at r equal to r plus. R plus means that you are here. So you will get the flux from this equation equated to the flux from this equation when r equal to r capital. And what's the other condition? The other condition is the current in the, let's say, total current or current in the positive j direction. So this is positive j. So the current here in the minus, and this is the current in the plus. So the current in the plus is just equal to the current in the minus plus the source coming from the shell. Because if you are standing here, the neutrons that goes from in this direction are coming from whatever inside plus whatever the source will produce. So you'll have those two conditions. then you will be able to calculate the constant. Yes.
Would the source be over 2? Would it be half of the source if we're assuming it's isotropic?
Yeah, you can. If the source is emitting this way and this way, yes. If not, okay. But just try S or S over 2, and then that's it. You will get yes.
How come as the flux goes to, or as the R goes to 0, how come the flux is 0?
What do you say?
How come the flux is 0?
I need a finite flux here. I do not need a buildup of flux. So this is just a source, and let's say a big shell like this, and you have neutrons. The neutron will penetrate. Although there is neutrons everywhere, neutron will penetrate here, and also neutron will leave here. So you do not need the flux to be of infinity at r equal to 0, because this at r equal to 0 will give you infinity. This equation will give you infinity at 0. So you need a finite flux in the center. So I will say, okay, finite flux, I can make the finite flux to be 0. It's just a mathematical trick to see what the value. I do not have any value for the flux. Otherwise you have to substitute with a value here. Let's assume that where is the equation? Here. So I will say it's equal to value. I don't know what's the value. I said, okay, finite. I will take it to 0. Yeah.
Couldn't you say the current at r equals 0 equals 0 and solve it using that?
How you will know that the current is at r equals 0 is equal to 0? It's the same, exactly the same, but it's the, instead of current means a vectorial quantity. I do not want to get into lots of complication. I just use the flux. So the flux is finite at r equal to 0. So finite at r equal to 0, this entails that, okay, C1 is equal to C2. And again, if you take sinh, if you look at the sinh function at r equal to 0, this will give you, this is cosh, and the sinh is like this. So the sinh is equal to 0 at 0. So again, this is just a mathematical trick. I don't know. Of course, in physical reality, there is some value for the flux. What's the value? I do not know. Yes?
Are you saying that J plus is the current going out from the surface and J minus is the current going out from the origin to the surface?
No, I mean this is J plus for all, but this is the minus and this is the plus. So this is J plus, all in this direction, but this is J minus means minus R, and J plus is plus R. In the region minus R inside the sphere and plus R outside the sphere. Okay, so this is R, and this is minus R, this is plus R. Thank you. So I almost solved the problem for you guys. So let's continue what the business that we used to do last time. So now, last time we showed that the flux as a function of energy can be given as Ck with K, where K is the isotope number K that contribute the most to the slowing down. So this is Ck over sigma scattering K as a function of energy E, and 1 over E. Okay, guys? Now, how can we relate this Ck to the slowing down density? Q of E and T and R. Who knows what's the Q? Q of T, E, T, and R. I defined this several times ago. Several times, long time ago. Slowing down number of neutrons per centimeter cube. So it's a density that slows down below energy E from above energy E at time T. Yes, at position R. Okay, guys? So how we will correlate Ck here with 5E? So we knew that The flux is per unit centimeter square, but the slowing down is per unit what? Volume cubed. So how will correlate this? So we will plot something like this. So here is the energy E of interest that I want to calculate the Q beneath it. Means how many neutrons are slowing down beneath this energy E. So when they will slow down to energy E prime within delta E prime, and this is alpha E prime. So I want you to look at this. This is, by the way, E double prime. E prime is here. So what's the minimum energy the neutron can come from if it will end up in one collision at energy E? Huh? No, it's not alpha E. E over alpha. So if a neutron comes from here in one collision, it will be E over alpha multiplied by alpha, so you will reach to this point. So this is the minimum energy in one collision that you will reach. So you have to come from E over alpha. Okay, and if you are coming from E, what's the minimum energy that you will reach to in one collision? Alpha E prime. Yes? So you will be here, alpha E prime. Okay guys, did you understand this? So now, if I am at sigma scattering for isotope J at E prime multiplied by phi at E prime multiplied by dE prime divided by 1 minus alpha J multiplied by E prime. What's this? This is the total number of neutrons. Yes? Total number of neutrons what? That will do collision at what energy?
E prime.
E prime. This is the number of collision that E prime multiplied by the probability that they will go from E prime to, let's assume that they will go from E prime to E double prime here. Okay guys? Actually this should be E. So this is the probability that they will go from E prime to E. Who has the book? I want to check the... Yeah, it's E prime, because the probability goes like, the probability B of E goes to E prime does not depend on the final energy E prime, it depends only on the initial energy, which is 1 minus alpha E. This is the probability. So this is E prime. Okay guys? Now, so this is the probability that you will go, let's say, you will go to a final energy, E double prime. It does not depend. Yes, the final energy, the probability does not depend on the final energy. Depend only on the initial energy. Let's assume that you have sigma scattering of E prime, phi of E prime is total number of collision here multiplied by the probability that you will go from here to here in one collision. This is the probability, does not depend on the final energy, depend only on the initial energy. So this is this one. So I want to get all the number of particles that will come from here to here and they will reach to this location. So I should run the integration from where to where? From here to it? Here. Yes, guys? Because maybe you are coming from here, maybe you are coming from here, and because we are looking for any numbers of neutrons that come or slow down from any energy above E, so we have to integrate from E to E plus E to E over alpha. Okay, guys? Okay? So what this give me? This give me total number of neutrons. Yes? That in one collision, anywhere from E to E over alpha will reach to E double prime. Yes? But I am interested in knowing total number of neutrons that will go beneath E. Yes? So I have to integrate E double prime from where to where? Alpha E prime to where? To E. This number is what I got in this bin. What I got from alpha E prime to E, I have to integrate over dE prime, and dE prime will go from where to where? Alpha E prime to E. Did you get it, guys? So this will be what? Alpha E prime to what? To E, and dE double prime will be here. Okay? But this is just for one isotope, so I have to take what? Summation over all isotopes. J. Okay, guys? And this will give me what? Q of E. So if you see this and if you see this in Stacy, do not panic. This is the explanation here. Did you understand now how we get it? We got energies at E prime that will slow down below E to E double prime, and this is this part here. So we have to integrate from E to E over alpha. Now I have to put alpha J, and alpha J. Okay, guys? So those are coming from the slowing down on isotopes J. Okay? Now, what we did last time, can somebody remind me what we did last time to solve this? Yeah, to solve, I want to solve this to get Q of E. What Q of E? What form? Q of E is equal to this stuff here, this bulky stuff here. What we did last time? Last time we said, okay, one of the isotopes will be the dominant isotope in slowing down. The rest of the isotopes will be with higher A atomic mass number. So if the cross section of all the isotopes will have the same form, will have pretty much the same form of energy, same shape of energy, I can take sigma scattering of E prime, phi of E prime divided by E prime, and I can take it outside the integration because I will evaluate it now at what? At E instead of E prime. Yes? This is what we used to do for the last couple of lectures. This is called similar cross-section form of variation of energy. This is just an assumption. So we can take this one outside and we will be left with dE prime over E prime, for example, from E to E over alpha J. Okay? Then once you will have it, this will be a constant, and you want to integrate a constant over what? dE double prime. What's the constant multiplied by dE double prime? So you will take the constant outside, then you will integrate over dE double prime, then you will get a bulky formula. So this formula is just summation of J 1 plus alpha J ln alpha J over 1 minus alpha J, all multiplied by sigma scattering J divided by sigma scattering. Okay, guys? And this is multiplied by C here. And so this term, you remember the first or the second chapter, we used to have this. Do you remember what's this? I told you this.
Like the average number of collisions.
Average logarithmic decrement.
So average logarithmic energy loss per collision. This is the logarithmic energy loss per collision, average logarithmic energy loss per collision. Okay? But now, your average logarithmic energy loss per collision, you will multiply it by, so this is J, for the isotope J. Now, you are multiplying this by sigma scattering of the same isotope, and you divide by all total sigma scattering. So what are you doing here? So let's assume that I have 4 isotopes, uranium-235, uranium-238. I have, let's say, oxygen. I have this, I have that. Let's say I have uranium-238, and I have oxygen, and I have hydrogen, let's assume, and I have carbon, and so on. So all what you will do is you will say, okay, this is Xz of oxygen multiplied by sigma scattering of oxygen over sigma scattering for all the isotopes, plus Xz for carbon multiplied by sigma scattering for carbon over sigma scattering for all isotopes, plus Xz for hydrogen for sigma scattering for hydrogen over sigma scattering for all isotopes, plus for uranium. So what are you doing here? Huh? All of this will give you an average for all the isotopes inside the reactor. So this is called what? So now, we reach to a conclusion that the slowing down as a function of energy is just equal to what? It's just equal to what? Some constant. Guys, is equal to what? Some constant multiplied by what? The average Xz as a function of energy. So the slowing down is just some constant multiplied by what? The average logarithmic energy loss per collision, average over all isotopes. Okay? Okay, guys? So Xz alone, what's Xz alone? Is ln what? Delta E over what? Over E, and you integrate from what? Alpha E over what? Do you remember this equation? This is the energy loss per collision divided by what? The initial energy, and this is the logarithmic energy. So this is the average logarithmic, and you multiply this by the probability distribution function. B of E goes to E prime dE. So this gives you the Xz. So Xz is the average logarithmic energy loss per collision. But this one is the average logarithmic energy loss per collision average over all the isotopes. Did you understand the difference? This is per isotope. This is average over all isotopes. Did you have any questions so far? Guys, do you have any questions so far? And this C is just 5E sigma scattering of E multiplied by E. So the flux as a function of E is just equal to Q as a function of E divided by dc sigma scattering of E 5E. Now, how many cases we solve it so far? So far, this is the distribution function of energy for the flux. Let's assume this is 5E, and this is energy E. And this energy of the fission, it takes the form of what? Chi of E. Then it goes like 1 over what? 1 over E, then a Maxwellian. We did not yet get to this part, so we solved the balance equation, steady state balance equation. We showed that at the very early beginning of this chapter that the flux goes like chi of E. Yes? In the energy region here, slowing down region, we solved the first case. And the first case was what? Slowing down only on hydrogen. Without what? It was with absorption, I think. Then the second case was what?
Slowing down without hydrogen. Or
So slowing down without hydrogen and without absorption. We neglected what? Absorption. Okay, guys? And from this case, for the hydrogen case, we showed what? The flux as a function of energy goes like what? 1 over sigma what? Sigma absorption of energy plus sigma what? Scattering for the hydrogen of energy multiplied by a constant. And all of this is multiplied by E, and it is modified by e to the power of minus something. This is for hydrogen. Yes, guys? When we look at the case where it's not hydrogen, it's bunch of isotopes, and there is no absorption, we reach to the conclusion that the flux of energy is like what? Yes? And we just show that the Q of E is just what? Over there. What's Q of E? Some constant multiplied by Z average of E. Now, the third case we will study now is the same like this one. Slowing down without hydrogen. Here we neglect absorption. Here we will have weak absorption. So we studied this case. We have two situations in this case. One is you are way above what? Your energy above 50 kilo electron volt. And then we studied the case where you are less than, this is above 1 MeV, sorry. The first case was above 1 MeV, and the second case you were what? Less than 1 MeV, but you are above the 50 MeV again, 50 kilo electron volt. So for this one we showed that it is exactly what? Chi over E. For this case we showed that it is the larger equation that contain chi of E and the other integration, and we said we have to do what? Iteration so that we'll be able to get the actual flux. But we said for a good estimation, as long as you are above 50 kilo electron volt, your phi of E can be represented as chi of E over a constant or over a sigma or something like this. And then here in this case we study the slowing down with hydrogen, slowing down without hydrogen, without absorption, slowing down with a weak absorber, which we will study right now. So now, the absorption, what's the importance of absorption in this case while you are slowing down? What absorption introduces in the formula here? What do you think? Absorption do what? What?
Resonance?
No, I'm not talking about resonance right now. While you are slowing down, if there is no slowing down and there is no leakage, we are infinite system. So if you are slowing down from energy, upper energy here, E prime below this energy E, and let's say this is alpha E prime here, this is E prime, this is E double prime again. So if you are slowing down below this energy E, so you will have, let's say, all the neutrons that will be generated in the fission, because there is no absorption and there is no leakage, they must reach to the thermal energy at the end. They must. Where they will go? They will not going anywhere as long as there is no absorption, there is no leakage. Yes? So you expect if you produce million neutron at the fission that you will get the million neutron at the thermal energy. But if there is fission, if there is absorption introduced in this case, so the absorption will decrease Q of E. And the farther your E is, the smaller Q of E. Why? Because you have absorption from all over until the fission energy. If you are near to the fission energy, the absorption will be a little bit. As long as you are decreasing in your energy, the absorption will increase and Q of E will decrease. So this is the effect of the absorption on Q of E. So now the time rate, the energy rate of change of Q of E will be equal to what? This is Q of E dE. This is what? Energy rate of a change of the slowing down. It's coming from where? I just told you 5 minutes ago. It's coming from absorption, guys. So this is the equation. This is the equation now. So whatever you absorb will change at the end the slowing down. Guys, you have to concentrate with me. Did you understand this? I know this course is not an easy course. Reactor physics is a tough course, and unfortunately all the books require that you have a good insight of what's going on, good physical background and mathematical background to understand. I try to make it easy. I don't know if I succeed in this task or not, but I try to make it easy. I try to even to explain between lines so that you'll understand, because the book does not explain this at all. Just will give you the equation then and split the other one, the final. So this is the time rate of change of the slowing down, the energy rate of change of the slowing down. So the slowing down as the rate of change of energy of the slowing down with respect to energy is equal to the absorption here. And again, now I can write my equation for slowing down in the medium where there is no hydrogen, bunch of isotopes that they are responsible for the moderation, and there is weak absorption. So last case we did not include absorption, so we will only for the balance equation. What's the balance now? Sigma absorption as a function of energy plus sigma scattering as a function of energy multiplied by what? By the flux as a function of energy equal to. We have a bunch of isotopes. This is a balance equation. Absorption at energy E, scattering at energy E will remove any neutrons from energy E. What comes to you, to your energy E, is the source. Yes? And what's the source now? Huh? No, it's the term that we have doing time and time again. Summation over all j's of what? E to what? E over alpha j of what? Sigma scattering at the energy E prime, phi at E prime, dE prime, divided by what? For j, divided by what? 1 minus alpha j multiplied by E prime. This is what? Total scattering at energy E prime from isotope j, multiplied by the probability that you will go to what? Energy E. It is independent of energy E. It only depends on the initial energy, which is what? E prime. So, but I have to count all the particles that come from all energies E prime up to energy E. Yes? So what's the minimum energy now that I will reach to? E. And what's the maximum energy? E over alpha. But alpha is coming from several isotopes. So I have to include what? J, and I'm summing over all isotopes. So this is just a balance equation, guys. All what I want you to understand, if this is the energy E, and you are coming from here, from energy E prime, the maximum limit for E prime will be E over what? E over what?
Alpha.
E over alpha. And all the particles that will be lost from E will be coming from two things. One is what? Sigma scattering, and the other one is what?
Sigma absorption.
I do not put anything because it will be absorbed here. So this is just a balance equation. Okay, guys? So now, if you will do the similar cross-section form variation for sigma scattering of E prime, phi of E prime over E prime, if you will take sigma scattering of E prime, phi of E prime divided by E prime, and you said that they have a similar form, so you evaluate this as at what energy? At E. You will be able to take this outside the integration, integrate with dE prime from E to E over alpha j, do the same thing, and finally you will reach to Q over zeta average over E. Okay, guys? So what will be the flux from here? So the flux will be equal to this divided by what? By this. So I introduced now, what's the difference between this and the case where I do not have absorption? So I added what? Absorption, yes, and I introduced I removed the constant C, and I represented the constant C by what? So the previous case was what? Flux equal to what? C over what? Sigma scattering of E multiplied by E. Yes? So what I did is I defined the constant C to be what? Q over C average. Yes? And I added the absorption from the weak absorption. Yes, guys? So the flux will be written as what now? Is this? I will remove this. So the flux will be what? E sigma absorption of what? Of E plus sigma scattering of what? Of E. Now, so we just define dQ by dE is equal to what? Sigma absorption of E multiplied by what? phi of E. Yes? Where is phi of E? So this will be equal to what? Q of E multiplied by what? Sigma absorption of E divided by C average E multiplied by sigma absorption of E plus sigma scattering of E. So this is a differential equation which is easy to solve. How to solve this equation? Separation of variables. So dq over q equal to this multiplied by dE. Yes? So if you solve this equation, you will get Q of E equal to Q at E1. You integrate from certain energy E up to E1, upper energy E1, multiplied by e to the power of minus E to E1, okay? Sigma absorption of E prime dE prime divided by sigma absorption of E prime plus sigma scattering of E prime, all multiplied by E prime. Okay guys, does it make any sense for you? Where the negative sign come from? Yeah, I flipped because the upper limit is a constant, is E1, and the lower limit is what? Is E. So if you integrate from Q of E, delta Q, from E to E1, this will give you what? Q at what? At E1. This is over Q. So this will give you what? Len Q from what? E1 to what? To E. Yes? So this will give you len Q of E1 divided by Q of E. Yes guys? But what you see here is Q of E over Q of E1. So you will flip this one and it will give you a negative sign. So now, if you want to calculate what's the slowing down at any energy E, it's very easy guys. This is what? E1. And this is energy what? E. If you want to calculate the slowing down that goes beneath energy E, all what you will do is calculate what's the slowing down at well-known energy E1 and then multiply by this attenuation coefficient that takes into account what's going on here, the effect of absorption on the slowing down. Makes sense? Yes guys? Do you have any question? Did you understand it or do you want me to repeat it again? If you don't understand it, do not be shy. Ask me and I will stop the lecture and I will tell it to you again or say it again. Do not be shy. There is no time to be shy during the class. You will lose your grade. I am not here to make it difficult. So it's better to understand it and go home while you are okay. I understand the material, other than it will be a disaster at the end. Did you understand? Okay. So this is the attenuation of the slowing down due to absorption. Again, so you can now calculate the flux again. We showed that the flux is what? The flux is this function. So I can remove Q of E and I can put what? This function. So it will be Q of what? E1 over XZ E sigma absorption of E plus sigma scattering of E, and this will be multiplied by what? By this factor. So it's a very similar to the first one actually. Yes? Very similar to the actual case. Yes? Very similar to the hydrogenous case. The hydrogen, I have what? I have sigma absorption, and this is sigma scattering of what? Of a hydrogen. And I have a constant, and what's the constant? Yes? E is outside the constant, of course. So it's a very, very much similar to the previous case of the hydrogen in shape. Okay, guys? So I will stop here, and next time we can continue in this, and hopefully we will get to the thermal energy region. So again, before you leave, fast energy region, chi of A. Moderation region, 3 cases. Hydrogenous material without absorption. Non-hydrogenous material without absorption. Non-hydrogenous material with absorption. Okay, guys? Then the thermal energy region. We will see that the flux will take the shape of Maxwellian. So now, the conclusion of this chapter is to show you that, okay, here is the flux variation in the 3 energy region of the nuclear reactor of interest. Why we are doing this? To get phi of E as a function of E, to be able to use it in calculating the average cross section, which is sigma scattering, let's say, or sigma of E multiplied by what? Phi of E divided by what? Phi of E to E. So you get this flux weighting function, substitute here, get the energy variation of the cross section. You will get an average what? Average cross section. Use it in what? D nabla square what? Phi minus sigma absorption what? Phi plus nu sigma fission average phi equal to 0. And this is average. All those average values are coming from this averaging. And in order to take this averaging, you have to understand what's the weighting function for the flux. Okay? Okay, guys? You will not find this in the book, at least in this area, in this first part of the book. But this is why we are studying this. Because you might ask why we are studying this. What the hell we are doing here? There's lots of complication. Here it is. Okay, guys? Thank you so much.